Hey guys, in this particular video I'll be showing you how to calculate the equation of motion for a pendulum. So let's get started. Let's say this is our pendulum right here, and this is a rope connecting a point mass of mass m, and our rope connecting it has a length L, which we're going to assume will remain constant. In other words, it won't stretch or it won't compress. Another assumption we're going to make is the fact that the mass of the cord, or the mass of the rope, is going to be so small it can be considered zero. So let me write that down. We're going to say that our length of our cord is going to be considered constant for simplicity's sake. We're going to say that the mass of our rope is so small it's going to be zero, and we're also going to assume the friction force, and this is the same for both air friction and friction in our pivot just here, is going to be so small that that's going to be considered zero as well. Alright, so in order to actually figure out the equation of motion that we're going to be solving for, we need to define a few terms. So let's get started. I'm going to define the angle between the vertical and our rope as theta. And my question to you is, what is the equation of motion? Basically, what is an equation relating theta to these variables I've got just here? Okay, so there are several ways you can do this, but the easiest way, I think, is using energy methods. So if you'll recall from a previous video, I derived that the change in mechanical energy is equal to the work done by non-conservative forces. Okay, well, what's a non-conservative force? Well, the non-conservative forces acting here will just be friction, and it will also be our normal force. Remember, we'll have normal forces acting on our pivot point just here, right, in both the vertical and horizontal direction. We'll also have air resistance, and we'll also have some resistance in the pivot point too. But like I said, our friction force is approximately zero, and because the normal force doesn't move our pivot point, that means the work done is going to be zero as well. So the total work done by non-conservative forces is going to be zero. Alright, if that was a little bit confusing, then I recommend you hit up my previous videos. Alright, well, that would imply that our change in mechanical energy now is going to be equal to zero. And what does that mean? That means that the amount of mechanical energy of the system in one state is going to be equal to the amount of mechanical energy in that system at any other arbitrary state, meaning then that our mechanical energy is just going to be constant. Alright, and if this, and I've gone through the basics of this in previous videos, so if you don't fully understand this, I totally recommend you hit up my previous videos. And what did we define mechanical energy to be? Remember, we defined mechanical energy to be equal to your kinetic energy plus your potential energy, right? And that's going to be equal to that constant. And for the sake of simplicity, I'm just going to call that constant K. Save me writing out the words every time. Alright, well, what's kinetic energy and what's potential energy? We should have a very good understanding of this by now. Kinetic energy is just going to be equal to a half mv squared plus mgh plus your elastic energy. I'll just write that as EE for now. And that's going to be equal to K. But notice I've assumed that the length of our cord will remain constant, right? That means it doesn't stretch and it doesn't compress. And that's the only thing which could be considered to be part of our elastic energy. So that means that's going to be equal to zero. Okay, so let's see if we can simplify this a little bit more now. Well, that would imply that we've got a half mv squared plus mgh is going to be equal to some constant. Okay, so it's very easy to just write kinetic energy is equal to half mv squared, and very easy to write gravitational potential energy as mgh. But what does it mean? Well, in order to know what it means, we need to look at our problem again. In this case, because the cord has no mass, the only kinetic energy we need to concern ourselves with is the kinetic energy of our point mass. And this is our point mass, and it's going to have a velocity in this direction, and it'll have a magnitude of r omega. Remember, that's r omega from our circular motion videos, because if you imagine, this is swinging out a circular type of orbit. Okay, not only that, but mgh, h is our distance from our axis, but we haven't defined an axis yet. So let's do that. Let's do that above. We could choose our axis anywhere, but for the sake of simplicity, I'm going to choose an axis up here. This will be y, this will be x, right? And our h is our vertical distance from our axis to our mass, but because our rope doesn't have mass, the only mass here is this point mass. So if you'll imagine it, I'm just going to redraw it just here. Our vertical distance h is this amount right here. This is h right here. And we know that this is L, and we know this is theta. So in other words, we know that h is going to be equal to L cosine theta, right? But it's not just L cosine theta. Because it's heading downwards and because we've denoted y as upwards, that means h is going to be equal to negative L cosine theta. Okay, so let's see if we can simplify this a little bit more now. We can write this out as a half m r omega squared plus mg times by negative L cosine theta, right? And that's going to be equal to that constant I was talking about earlier. So let's see if we can figure this out a little bit more. And I know I'm scrolling all over the place, but bear with me. All right, so that's going to be a half m. And what's r? What's r? Well, remember, r is your radius of your circle being swooped out, which in this case is just L, right? The length of your cord is the same as the radius at which it's swooping a distance, right? And remember, we're assuming that our mass ball is so small we don't need to concern ourselves with the radius of that. And that's going to be equal to a half m L squared times omega squared, or, as you'll remember, theta dot squared. Alright, and that's going to be equal to, and that's going to be added to minus mgl cosine theta, and it's going to be equal to k. Okay, let's see if we can figure this out a little bit more. In fact, let me zoom out a little bit. I feel like I'm too far in the screen. There we go, that way you can see a little bit more about what I'm writing. Okay, so let's see if we can figure this out. There seems to be no way we can solve for theta because there's some pesky little constant hanging on the right hand side, right? And there's no way to get rid of that unless you differentiate, right? So what I'm going to do is I'm going to differentiate both sides with respect to time. I'm going to differentiate both sides with respect to time, and I'm going to get a half m L squared theta dot squared minus mgl cosine theta is equal to your derivative with respect to time of k. Now what's the derivative of anything with respect to a constant? It's going to be 0, right? Okay, so that means we can simplify this now, and by grouping out the constant terms in here, remember L is constant and M is constant, that means we'll be given mL times by your derivative d dt of a half L theta dot squared minus, let's see, it'll be, we factor out the m, we factor out an l, so that'll just be g cosine theta, and that'll be equal to your right hand side, which I talked about was equal to 0. So this becomes really a matter of mathematics at this point. Okay, so let's see if we can figure this out. Well, we're left with two solutions here. We're left with either ml is equal to 0, or we're left with the derivative of this beast in the middle of these brackets, a half L theta dot squared minus g cosine theta is equal to 0, right? This is a really trivial solution, right? This implies that either m is equal to 0 or either L is equal to 0, neither of which are the case, right? So this is really just a trivial solution, and we shouldn't really pay attention to that. Okay, so let's see if we can figure out what this means. Well, let's see, we can distribute the derivative, and that becomes a half L times by d dt of theta dot squared, right, minus g times by d dt of cosine theta, and that's going to be equal to 0. Alright, let's see if we can figure this out a little bit more. I feel like I should zoom out just a little bit more. Okay. So this is a pretty difficult thing to analyze. I'm debating whether I should show you in this video because it's a pretty complicated piece of calculus. It involves a chain rule. I think I won't show it in this video, but I might do a link to how to solve these types of calculus problems in the description if you're lucky. So that'll be a half L times theta dot times by 2 times by theta double dot, right? And that's going to be subtracted from g times by negative theta dot sine theta. I know I've kind of skipped a few steps, like evaluating these derivatives right here. That's because I don't want this video to be too long, and I've also done these types of problems earlier in other videos. I might do a link in the description to show you how to do that. But in a nutshell, just take my word on it. Oops, that should be times by, and that'll you'll see that if you factor out a theta dot, we're left with L. Don't forget that these two cancel out. That'll be L theta double dot plus G sine theta. G sine theta is equal to 0, right? Notice that these negatives cancel each other out as well, meaning that we're left with another solution. We're left with theta dot is equal to 0, or we're left with L theta double dot plus G sine theta is equal to 0 as well, right? So in other words, we can write then that a solution is one possible solution is that theta dot is equal to 0. It's not an interesting solution. Imagine that's pretty much saying this thing's hanging limp and not going anywhere, which is technically true, but it's not an interesting solution. And another solution is that theta dot, once you put this on that side and divide by L, you can write theta dot is equal to minus G on L sine theta. This is a much more interesting solution, because it shows you it solves the solution for several different values of L, right? And this is your solution right here. This is your solution. I just going to put another box around it to make it a little bit more obvious. This is your answer. And for the sake of calculating what theta is actually equal to, it's reasonable for small angles to assume that sine theta is equal to theta. For small angles. I won't go into the mathematical proof of why that's the case, but that is the case for theta approaches 0. Alright, so that's one way you can solve this problem. Stay tuned, guys, and I'll show you a few other ways you could also solve the equations of motion for a pendulum.